Now we are ready to define a vector space or a linear space, which is the basic object of this topic, linear algebra. So, we will say this vector spaces. So, this is also starts with a non-empty set with some operations. A non-empty set V together with operations called addition and scalar multiplication. Scalar multiplication is a vector space over a field F if the following axioms hold. First one is this V with respect to this addition operation is a commutative group. Second property is that V is closed under scalar multiplication, that is, for any element u in V and alpha belongs to F, this alpha dot u belongs to V. Third property is this: for alpha beta in F and u belongs to V, alpha plus beta dot u is equal to alpha dot u plus beta dot u. Fourth property is for alpha belongs to F and elements u and w in V, alpha dot u plus w is equal to alpha dot u plus alpha dot w. Fifth property is that for alpha beta in F and u in V, alpha dot beta dot beta dot u is equal to alpha dot beta u. And this sixth axiom is this: 1 dot u is equal to u for every element u in V and 1 is the multiplicative identity of F. Multiplicative identity of this field. So, if a non-empty set together with two operations called addition and scalar multiplication, that is called a vector space over a field F if these axioms hold. here whenever this V together with addition and scalar multiplication is a vector space. So, if this is a vector space over a field F, then elements of V are called vectors, and elements of F are called scalars. So, we will have also linear combination of vectors, that for vectors v1, v2, vn in V and alpha 1, alpha 2 to alpha n in F, the expression alpha 1 v 1 plus alpha 2 v 2 plus alpha n v n is called a linear. Of course, this is also may be said as finite linear combination of v 1, v 2 to v n. Notice that if V is a vector space over F, then V contains all finite linear combinations, of elements in V. That is why V is called a linear space. That is why V is also called a linear space. Next we will have some example of vector spaces. So, the first example, that is a very natural one, is that set of complex numbers C is a vector space over the real field R, but the converse is not true, but the converse is not true. That is, R is not a vector space over C, because R will not be closed under scalar multiplication. So, the second example is basically that is called the n tuple space. The n tuple space that is for any field f, for any field f, Fn, that is Cartesian product of f with itself n number of times, that Fn consists of all n tuples, that x1, x2 up to xn, such that each xi is an element of f, is this Fn is a vector space over f with respect to the operations that for any two elements, that addition is defined like this: x1 x2 to xn plus y1 y2 to yn is equal to x1 plus y1 x2 plus y2 like this xn plus yn, coordinate wise addition. And scalar multiplication is alpha times this x1 x2 xn, that is equal to alpha x1 alpha x2 alpha xn for any alpha in f. So, here we can observe that this Rn is also a vector space, because so as a particular case Rn is a vector space over R. This Rn is also called that n dimensional Euclidean space. Next, we will have this example, third example, that is space of matrices. Space of matrices, that collection of some matrices also form vector space. So, here for any field f, let us denote that f m cross n be the collection of all m by n matrices over f. Then this f m cross n, this is a vector space over this field f with respect to matrix addition and scalar multiplication. With respect to matrix addition and scalar multiplication. So, next we will have this fourth example is this space of polynomials. Space of polynomials. So, let f be a field and P f be the collection of all polynomials over f, that is P f is the set of all polynomials like a0 plus a1x plus a n x to the power n such that each a I that comes from this field f I from greater than equal to 0 less than or equal to n, and this n is an integer that is greater than or equal to 0. So, this P f will be the collection of all these polynomials over this field f is a vector space over this field f with respect to addition of polynomials and scalar multiplication of polynomials with respect to addition of polynomials and scalar multiplication of polynomials, that is, if we are having two polynomials, that a0 plus a1x plus a n x to the power n plus another polynomial say b0 b1x up to say bm x to the power m, then their sum is the polynomial c0 plus c1x up to this c k x to the power k, where this c k is equal to, where this c I is, where c I is equal to a I plus b I for I greater than or equal to 0 less than or equal to k, and k is equal to maximum of n and m, and of course, this a I is equal to 0 for I greater than n and b I is equal to 0 for I greater than m. And for any scalar alpha, alpha into any polynomial, that a0 plus a1x plus a n x to the power n is equal to alpha a0 plus alpha a1 x, like this, alpha a n x to the power n. So, then we can have some natural properties of a vector space that we will write in a lemma, and then of course, the proof of this lemma is not difficult to check, and one can take this as an exercise. So, these properties are very trivial, but useful. We use them again and again. So, if V is a vector space over a field F, then we will have the following results. A is this: alpha dot 0 is equal to 0 for alpha belongs to F, and 0 is the additive identity of V plus called the 0 vector. Second property we can have is this 0 dot any vector v that is equal to 0 for any vector v in the vector space, and 0 in LHS is the scalar 0 and 0 in RHS is the vector 0. Third property we can have is this minus alpha into V is equal to minus alpha V for any alpha in the field F and vector V in the vector space. Fourth property we can have is this if V is not equal to non-zero vector not equal to 0 or a non-zero vector in V, then alpha dot V is equal to 0 implies that alpha equal to 0. That means, for any non-zero vector V, if this alpha dot V equal to 0, then alpha equal to 0 for any alpha in F. So, then next we will have this subspaces concept. Whenever we are having some algebraic structure, we have its substructure. So, we will have this subspaces. So, let V be a vector space over a field F, then a subset W of V is called a subspace if W is closed under the same operations in V, that is addition and scalar multiplications in V. In other words, for U V belongs to W and alpha belongs to F, U plus V belongs to W and this alpha U belongs to W. Plus and this dot, plus and dot are the operations of V. One can also combine these two and write in a single condition that combining the above two, we can also have that W is a subspace of V if for U V belongs to W and alpha beta scalars, alpha U plus beta V belongs to W. So, let us see some example of subspaces. Let us have some example of subspaces. So, that trivial subspaces are if this 0 is the 0 vector of this is the 0 vector of V, then this set consists of the 0 vector only is this is a subspace. This is the subspace of V called trivial. Called trivial subspace. Similarly, the vector space V, the vector space V itself is a subspace. Subspace of V and is also called a trivial subspace. So, next we will have another example. Let us consider this R 2, V will take this Euclidean plane R 2, then this for any point A B in R 2, the line joining the origin 0 0 and this point A B is a subspace of R 2, that is this subspace can be written as set of all x y in R 2 such that A x plus B y is equal to 0. However, if we consider any other line that is not passing through the origin, however, this line, that collection of all x y such that A x plus B y is equal to 1, this is not passing through origin, is not a subspace of R 2. So, next we will have different kind of vector space and subspaces, that is they are matrices. So, now you consider this set of all m by n. Okay, let V be the space of this n tuples. Okay, no, we will consider this V with this set of all m by n matrices over F. Then the collection of all with this m by n matrices with m is equal to n. Then this set of all n by n symmetric matrices form a subspace of V. Then the collection of all n by n symmetric matrices over F forms a subspace of this V. Similarly, we will have another example, that fifth example, that the set of all Hermitian matrices, let again we will consider this vector space V be C n cross n, or in other words the collection of all n by n complex matrices. This is the collection of all n by n complex matrices. Then here the collection of all n by n Hermitian matrices. Hermitian matrices is not a subspace, of V, because the diagonal entries of these matrices are real and will not be closed under scalar multiplication. If the scalar is purely a complex number, So, these are some example of subspaces. Then we will define another important concept, that is a linear span of a set, of vectors. So, let us have a vector space, let V be a vector space over a field F, and S be a set of vectors in V. So, let us denote, let L S be the collection of all finite linear combination of elements in S. Finite linear combination means linear combination of finite number of elements in S, that is linear combination of all possible finite subsets of S. Then this LS satisfies some properties that again we will write that as a lemma. Of course, this proof is easy and that has been left as an exercise. It is not difficult to check that first property is this: LS is a subspace. LS is a subspace of V, and second result that one can see is that in fact not only this is a subspace, this LS is the smallest subspace of V containing S. LS is the smallest subspace of V containing S. In other words, that is, whenever the W is, that is, if W is an arbitrary subspace of V containing S, then this LS will be contained in W. This is what we mean, that this LS is the smallest subspace. It will be contained in a subspace if that subspace contains this set S. So, let us have some examples. So, first example is that we can take this vector space as R2 and this S is consist of only one element or one vector of this vector space, that is 2, 3. Then LS is actually the straight line passing through origin and 2, 3. Then LS is the straight line in R2 passing through the origin 0, 0 and 2, 3, this point. Second example is that again if we take this V is equal to R2 and S is consist of the points 1, 0, 0, 1. Then LS is equal to the whole space R2. So, this linear span of sets will be useful, and this LS is also called the subspace spanned by S. LS is called the subspace spanned by the set of vectors S. Then we will discuss about linearly dependent and independent of vectors. So, that is very important concept in a linear algebra. Linearly dependent or independent of vectors. So, this is a very important concept in linear algebra. So, we give this definition. So, let V be a vector space over a field F and S be a subset of V, subset of V. S is said to be linearly dependent, said to be linearly dependent if there exist vectors v1, v2 to vn in S and scalars alpha 1, alpha 2 to alpha n, not all 0 of course, alpha n not all 0. This is very important, such that this linear combination alpha 1 v 1 plus alpha 2 v 2 plus alpha n v n is equal to 0. This 0 is the 0 vector. If S is not linearly dependent, then it is called a linearly independent set. Linearly independent set. Here we will have some results on this linearly dependent and independent sets. They are trivial. So, we can write them as a remark sort of thing. Of course, these are trivial. Trivially one can get using the definition of linearly dependent and independent of vectors. So, first one is like this: a superset of a linearly dependent set is linearly dependent. And similarly, we can have that a subset, every subset of a linearly independent set is linearly independent. And third observation one can have is this: any set which contains the 0 vector, is a linearly dependent set. Linearly dependent set because alpha dot 0 equal to 0 for alpha not equal to 0 be a scalar. Then fourth remark we can have that here one can check this, I mean linearly dependency of a finite number of vectors. Suppose a finite number of vectors are given and we want to check whether they are linearly dependent or independent. So, how should we do? What is the working formula for that? So, this is all about the definition that we have given, but how to check? I mean what is the method for checking whether a given finite set of vectors are linearly dependent or independent. So, using this definition also one can check directly, and we will also give another method for verification of linearly dependent and independent by using some special type of matrices. So, here we consider that let that S be a set of vectors that V1, V2 to Vn be a finite set of vectors in V. So, to check whether S is a linearly dependent or independent set, we do the following. That is, we consider a linear combination of vectors in S and equate to 0. Take this alpha 1 V1 plus alpha 2 V2 plus alpha n Vn equal to 0, where alpha i's are scalars and will be determined. So, if we can find that all scalars are 0, scalars alpha I are 0, say this be equation 1 by solving equation 1, then then the given set S will be linearly independent. Otherwise, it is linearly dependent. So, let us take one example and explain this concept, that you take here V be R3 and S1 be this set of vectors 1, 2, 3, 1, 0, 2, 2, 1, 5 and S2 be this set of vectors 2, 0, 6, 1, 2, minus 4, 3, 2, 2, be subsets of V. So, we will check linearly dependency or independency of S. So, for S1, consider this alpha 1, 1, 2, 3, alpha 2, 1, 0, 2 plus alpha 3, 2, 1, 5. Take this linear combination of vectors in S1 and equate to 0. Then we will get equations like this. Then we get equations alpha 1 plus alpha 2 plus twice alpha 3 is equal to 0, twice alpha 1 plus alpha 3 is equal to 0, 3 alpha 1 plus twice alpha 2 plus 5 alpha 3 is equal to 0. On solving this system, on solving these equations, we get alpha 1, alpha 2 are all and alpha 3 are all equal to 0. Therefore, this S1 is a linearly independent set. However, for S2, we can take alpha 1 is equal to alpha 2 equal to 1 and alpha 3 equal to minus 1 and get that this alpha 1 times 2, 0, 6 plus alpha 2 times 1, 2, minus 4 plus alpha 3 times 3, 2, 2 is equal to 0. So, S2 is a linearly dependent set. This is a linearly dependent set. So, there is another way also to verify that whether the given set of vectors are linearly dependent or independent, and for that we need a type of matrix that is called echelon matrix. So, here we give this definition of an echelon matrix. So, an M by N matrix A is said to be in echelon form, said to be in row echelon form, if it satisfies the following, that first condition is this: all the 0 rows of A are at the bottom of A, and second is this: for all the non-zero rows of A, as the row number increases, the number of zeros at the beginning of the rows also increases. So, let us see one example here, how to apply this echelon matrices and verify whether a given set of vectors are linearly dependent or independent. So, let us take V be the vector space R4 and S be the set of vectors that 1, 2, 1, minus 2, and this 2, 1, 3, minus 1, 2, 0, 1, 4, and S prime be the set of vectors 0, 1, 2, minus 1, 1, 2, 0, 3, 1, 3, 2, 2, 0, 1, 1, 1. So, let us verify whether they are linearly dependent or independent sets. So, for this set S, this subset S of vectors, we form a matrix by taking the vectors in S as rows. So, from S form matrix that 1, 2, 1, minus 2, taking the vectors as rows of this matrix, and that 2, 0, 1, 4. So, applying this elementary row operations or replacing R2 by R2 minus twice R1, we get this matrix that 1, 2, 1, minus 2, this is unchanged, and 0, minus 3, 1, 3, 2, 0, 1, 4. So, again from this matrix we can have this elementary row operation R3, that we replace R3 by R3 minus twice R1 and get this matrix 1, 2, 1, minus 2, 0, minus 3, 1, 3, 0, minus 2, minus 1, and 8, and again by elementary row operations, that R3 we replace by this 3 R3 minus twice R2 and we get this matrix that 1 2 1 minus 2 0 minus 3 1 3 0 0 minus 5 18. The last matrix is in echelon form. Here there is no non-zero row, there is no non-zero row. So, S is a linearly independent set, linearly independent set. Similarly, one can get this echelon form of S prime like this. Similarly, we get an echelon form for S prime as this 1 2 0 3 0 1 1 1 0 0 1 minus 2 0 0 0, where there is a 0 row. So, S prime is linearly dependent set. This is how we verify that whether a given set of vectors are linearly dependent or independent by using this echelon form of matrices, that given any set of finite set of vectors, we form a matrix by taking the rows of the matrix as the vectors in that set, and we convert to echelon form. If in the echelon form all the rows are non-zero, then this set will be linearly independent, and if there is a 0 row, then this set of vectors will be linearly dependent set. Of course, we will repeat this echelon form again in our next lecture while finding basis and dimension of vector spaces. Okay, that is all for this lecture. Thank you.